Let's look at an example problem that involves discrete time convolution. So I'll work a problem from the end of chapter 3. This is problem 3.8-1. It's a fairly complicated problem. We're told that our h of n sequence is minus 2 to the n power times u of n minus 1, and our input signal x of n is e to the minus n u of n plus 1. Okay. If I sketch, for example, x of n here, it actually, because of the argument here, it's going to be non-zero for n equal minus 1, and it would be e to the minus 1, or that sample would have a height of e. If I plug in 0 here, e to the 0 is 1. If I plug in 1, I get e to the minus 1, or the reciprocal of e. Okay. So I can see that this x of n, actually I'm going to call it x of m, because this will be the notation we'll use in our convolution sum. So x of m looks like this. It's this e to the minus m times u of m plus 1. Let me squeeze that in right below that, because I want to draw the h of n sequence here, or again, actually the h of m sequence. Now, it involves a unit step that shifted to the right, whereas x of n involved the unit step that was shifted to the left. So the first non-zero term here will actually be at n equal to 1. So it's 0 at n equal to 0, or again, I'll do this in terms of m. At 1, we've got minus 2 to the first power, so that's actually a minus 2. And then at 2, I'll have minus 2 squared, which is 4. At 3, it would be minus 8. And this is what x of m looks like. I'm sorry, this is actually h of m. Yeah, h of m. It's minus 2 to the m times u of m minus 1. So again, it's going to be helpful to take some of the same steps that that we did with continuous time convolution. The summand here looks very similar to the integran that we used in continuous time convolution. So we want to time reverse and shift one of these functions. Again, the argument is usually we'll time reverse about the origin, the simpler of the two functions, and then shift that. And so I'm going to choose to time reverse and shift my x of m function. And so what I want to draw here is x of n minus m. So what that'll look like, again, it's the origin now that's shifted to n. And when I and here this is the sample that has a height of 1. The sample here that has a height of e would actually be at n plus 1, and the one now that has it's equal to 1 over e would actually be at n minus 1. This goes on forever in this direction, but is equal to 0 for all m values greater than n plus 1. And it's helpful here to have the mathematical form of x of n minus m, and so I'll just substitute n minus m in for m. I get e to the minus n minus m u of n minus m plus 1. So this is what this looks like. And again, if you remember from our convolution formula, that I'm summing the product, summing from minus infinity to infinity of the product of these two sequences for different values of n. Okay, and again, for the case where n plus 1 is less than 1, or n is less than 0, there's actually no overlap between these. As long as n plus 1 is less than 1 or n is less than 0, there's no overlap, and in that case the product would be 0, the output sequence would be 0 everywhere. Okay. Now let's take a look at what happens for n greater than or equal to 0. Now this sequence will actually be shifted out here. N plus 1 will be greater than or equal to 1. And now my convolution sum on the lower limit, I'll be summing from m equals 1, because my h of m function is 0 for all m less than 1. And then I'll be summing up to n plus 1. So because this time reversed function is 0 for all values of m greater than n plus 1. And then I'll have, in here, I'll have the product of these two. I'll have minus 2 to the m, and I'll have e to the minus n minus m. I'm going to leave out the unit steps because they were actually used to determine the limits here on this summation. Okay, so I can pull out, I'm summing over m, so I can pull out this e to the minus n term, e to the minus n, have my summation from m equal 1 to n plus 1, and then here I've got minus 2 to the m, and here I'll have e to the m, so I can combine those as minus 2e to the m. Okay. On the convolution handout, on the back side now, you've got a table of summations, okay, as well as a table of discrete-time convolutions. This summation is one of those that is listed in the table, and so from using the table I can get, again, for case where n is greater than or equal to 0, I get the output is e to the minus n, and then that summation I can write as minus 2 e to the n plus 2 minus 2 to the e times e to the first power all over minus 2e minus 1. Make sure you verify this again from that summation table. With a little algebra I can simplify this a bit, perhaps it's a bit simpler, and write this as 2e squared over 2e plus 1 all times minus 2 to the n plus 1 minus e to the minus n plus 1. Okay. And this is valid for all n greater than or equal to 0, so I can actually use a unit, just multiply by a unit step to get a solution then that's valid for all n, because the unit step, since it's 1 for n greater than or equal to 0, this is just multiplied by 1. For n negative, it would be multiplied by 0. And so this is a form of the output for over all values of n. Another way I can do this is actually using the discrete time convolution table. Again, I'm dealing with shifted functions here, so I have to do a few convolution tricks. I'll actually define w of n as being minus 2 to the n u of n times our unit step. Since our impulse response was actually minus 2 to the n u of n minus 1, I get that h of n is related to w of n. It's just minus 2 times w of n minus 1. So h of n is just a amplitude scaled shifted version of w of n. Okay, and actually I need parentheses around here. And then similarly for I can define a new sequence, an unshifted sequence, since that's all that's in the table, that z of n is e to the minus n u of n, and since x of n was defined as e to the minus n u of n plus 1, then x of n is related to this unshifted function z of n. You can see that it's just e times z of n plus 1. Okay. But the reason I do this is because I can find the convolution of w of n and z of n, these two unshifted functions. They're in my convolution table. So from the convolution table, I get that w of n convolved with z of n. These are two exponential sequences. So this is directly from the table, and just plugging values into the table. In one case, I'll have a gamma 1 is equal to minus 2, and the gamma 2 value would actually be e to the minus 1, and then plugging those values directly into the table, I get minus 2 to the n plus 1 minus e to the minus 1 to the n plus 1 all over minus 2 minus e to the minus 1. So this is the convolution of w of n and z of n. I really want the convolution of h of n with x of n. Well, h of n is shifted 1 unit to the left. It's a shifted version of wn. I'm sorry, it's shifted. H of n is wn shifted 1 unit to the right. X of n is equivalent to z of n, but shifted 1 unit to the left. A shift to the left is going to cancel out a shift to the right. So h of n convolved with x of n is going to be an unshifted version of this. The only thing I have to take into account is this amplitude scaling. Multiplication by minus 2 here and e here. Taking that into account, I get y of n. Multiply the minus 2, that'll cancel the minus signs here. I get 2 over 2 plus e to the minus 1. And then I also have the multiplication by e. And then I get minus 2 again to the n plus 1 minus e to the minus 1 to the n plus 1. And this should have a u of n associated with it. that's in the table, so this should also have a U of n. If you compare these, you'll see that this result that we get from the convolution table is identical to the result we get by direct evaluation of the convolution sum.